Scoot forward. Come up closer, please, if you can. All right, here's what we're going to do. I want to take a look. I want to sum up everything we did yesterday, and then we're going to take one step forward from where we were yesterday. And then I'll give you a day tomorrow to work on stuff. How's that? Okay, so phone should be away, please, like completely away. All right, so we want to summarize everything that we've done so far. Everything that we've done so far with our transformations, we can summarize in one little statement here. We're going to call this like our transformation template. So if our parent function, if we'll call p of x is the parent function, right, meaning where we start, then if we want to do some transformations to create a new function f of x based on this, everything that we've done can be summarized by this statement. Right? Okay, so what are the A and the H and the K?
The H is your this movement.
Okay, it's horizontal
K is
shift
your
or translation. K is the vertical shift, right, or translation. And what's A again?
The one that does you can like manipulate.
A does a couple things, doesn't it? A can, if it's negative, it's going to reflect vertically, right? Positive, it doesn't. If it's bigger than 1, it's going to stretch. Hold on, please get rid of that. It's going to stretch vertically. If it's bigger than 1, its absolute value is bigger than 1, right? If its absolute value is less than 1, it's going to compress. So what we could call A, the dilation factor, right? Think back to geometry. Remember talking about dilations. Dilations, if you took a small, like a square or rectangle, and you dilated it, you just either enlarged it or you shrunk it, right? But it stayed the same shape. Would you agree? Okay, so this is like that. It's like we're going to dilate the function vertically. We're either going to stretch it out vertically or we're going to compress it vertically. If it's negative, we actually reflect it then too. Okay? So those three numbers tell us everything. So what if we wanted to do something like this guy right here? If we want to graph this guy, so this is based on what parent function? What would p of x be here? What kind of a function is that?
Absolute value.
Absolute value, good. So the parent function is just the absolute value of x, right? So let's just identify what are the values of those three parameters that we just looked at. Let's start with h and k because they're the easiest. So what are h and k? H is -1, right? Because it's the number, remember, h is the number that's being subtracted from x, right? Okay? So the value of h is -1 and k is -2. Okay, so what is significant about that for an absolute value function?
That's right. It's 1/5.
Well, okay, that's the starting point. That's the vertex, isn't it? Because whatever point starts off at the origin with our parent function is going to end up there, isn't it? Right? So that's the vertex. Right there. Okay? What about the 1/5? What's that telling us?
The y values.
Okay, so we know A is 1/5. What does that tell us? It is. It's showing us the value of a point other than the vertex, right? It's telling us that whatever we would have normally expected from our parent function for the change in y from the vertex, we're going to multiply that by 1/5, right? So if we were going to graph this thing, and let's do that. I just want to make sure everybody gets this. And I know you guys are using a good trick here. You're using slope, but I'm going to give you an example today that shows you why that's not always going to work. It's a great trick for this type of function, but it doesn't work in all cases. Let's see, where's that guy? That's what I want. But what was my function here? It was 1/5 square root of x plus 1 minus 2. Okay? So So look what we did here, right? There's our vertex. Like you said, it went back 1 and down 2. You already told me that the coordinates of the vertex were -1, -2, right? Good. Okay, let's look at a couple other points. So there's the vertex of the red function and the blue function. Another point on the red function, if I go over by 1, I go what? Up 1, good. Okay, we got to make these red too. There we go. Okay, and one more. What if I went over by 5?
5.
I'd go up by 5, good. Okay. Okay, now what about some points on the blue function? Well, you already told me that the vertex is at -1, -2. Okay, those were the values of h and k, right? Okay, so if I go over 1 to the right, let's look at this. If I go over 1 to the right from the vertex, on my parent function, if I go 1 to the right, I would normally expect to go up by 1, right? So, I gotta be able to write on here. Okay, so we would expect to go over 1 and plus 1. That's what's normal. Right? That's not what we do, though. When we go 1 to the right, how much do we go up?
1/5.
1/5. Because we're going to multiply the normal amount times a. Right? So that's not a very convenient place to pick. What's one that we should pick?
4, 1.
Okay, we want to pick a normal value that's a multiple of 5 because we want to think of numbers. We're going to multiply the normal changes in y by a, which is 1/5, right? What kinds of numbers? Give me examples of numbers you could multiply by 1/5 conveniently and not get fractions. 5, 10, 15, multiples of 5, right? For our function, and what we really want to think about is we want the normal increase in the function. We'll get rid of that anyway. We want the normal increase in the function to be a multiple of 5. So we got to think in terms of our function. If I want the change in y to be 5, that means I would have to go over 5 to the right. Everybody agree? For the normal function, I would do this. I would go right 5 in order to go up 5, right? So this is a vertical dilation. So we're saying if we do the same, if we move the same distance sideways from our new vertex, how much are we going to move up? Well, I'm going to move up 5 times a, which is 1/5, right? So I just go up by 1, and there's my point. See how that works? Okay. You've probably seen that you could just say, okay, to get another point, I could treat this like a slope, and you can't. From this point, I could just rise by 1 and run by 5, and it's going to get me there, isn't it? Right? That's a great trick. It works for absolute value functions. Let's take a different kind of function, though. Let's take one like this. Okay, let's do one like this. Let's take a square root of x graph instead. Okay. Our parent function is the square root of x. Now, we're not going to officially deal with square root graphs for a while, but I want you to see something here. It's important that you don't just think about that as being a slope. Let's find some convenient points for a square root graph. So here's my function, right? I'm just going to input x values to calculate y values, right? So for example, if I input x equals 0, what's the square root of 0? 0. Okay, so we get the point x equals 0, output 0. Okay, that's what we call the initial point for a radical function, for a square root function. If I input a 1, that's convenient. Square root of 1 is 1. So I input 1, I output 1. Over 1, up 1. Now it gets weirder though. It's not a line. What's the next convenient input value for me? 4, because 4 is a perfect square, right? The square root of 4 is 2. So if I input a 4, I get back a 2. If I input the next perfect square, 2 squared is 4, 3 squared is 9, right? So the square root of 9 would give me 3. What would the next one be? Input 16, get back 4. Okay, so we could also go over 16 and up 4, right? Okay, so then what's going to happen here then? Now, what if I want to do, for this parent function, a square root graph, what if I want to do something like this? What if I want to, h and k are 0 here, aren't they? No numbers being subtracted from x, everybody agree? No numbers being added outside of the square root, right? If I were to write a template for a square root function, let's just do this real quick. If I were to write a template for a square root function, it would just look like same parameters, right? The a goes in front, h is what's subtracted inside the function from x, and k is what we add at the end, right? So for us, well, we're not, those are both 0. What is a? 2, right? So what's that mean? That means I should take all of my normal change in y's and times them by 2, right? So when I go over by, we know what this graph's going to look like, don't we? If normally I would go over by 1 and up by 1, I'm going to go up 1 times a. I'm going to go up 2, right? So that point's going to get stretched up to there. Normally I would go over 4 and up 2. I'm going to multiply that by 2, so I'm going to go up 4, right? Normally I would go over 9 and up 3, but now I'm going to go up 2 times 3, right? Which is 6, right? So it's going to be there. We see that? Okay. So it's not a slope this time. We actually have to think about it in terms of what's the normal value and then what am I going to multiply by, right? And if we show this one, we can see that's going to matches up perfectly, right? Okay. So let's try a trickier one. Let's try something like this. Instead of a 2, let's make that I'm going to make it a 2/3. That's pretty tricky. Okay, so what are my values? I haven't changed. H and K are still 0. Everybody agree?
Yes.
Okay. What's A this time?
2/3.
Okay, so somebody tell me a convenient point. Actually, just tell me a point for now. So tell me a point that's going to be on the I guess it was a green graph. Tell me the point that's going to be on, tell me a point that's going to be on the green graph.
0,
0, 0. There, winner. There you go. That's going to be on there for sure. So there's a green point. What if I went over 1? How far up would I go?
Up 2/3.
I'd go up 2/3. That's not very convenient. That's about right there-ish, right? Maybe. Okay, that one's not very good. If I go over 4, I'm going to go up, instead of 2, I'm going to go up 2 times 2/3. What's that? 2 over 1 times 2 over 3. Multiply straight across. 2 times 2/3 is 2 over 1. That's 2, right? Times 2/3 is what? 4/3. Okay. So if I, instead of going up 2, I should go up 1 1/3. So that's not a very convenient point. Is there any of that's going to be convenient?
Not really.
Oh yeah, there's one.
Oh, yeah, I see.
Which one's going to be convenient?
The next one.
The next one, right? Because on the next one, my normal change was plus 3, right? 3 is a convenient number to multiply by 2/3, right? How come? Because 3 is in the denominator. You kind of get the idea here, right? When we're picking convenient points to use for dilations, right? We want to pick points where the predicted change in y is a multiple of the denominator of a, right? Those will be convenient. Okay, so what about this one? If I normally go up 3, what's 3 over 1? That's 3 times a, which is 2/3. 2. Yeah, I get 6 over 3, which is 2, or I can even cross cancel and just get 2. That's great, right? That works. So that gives us a value over here at over 9. And the reason I picked 9 is because 9 is what would have given me a change in y of 3, right? Increase in y of 3. So now it becomes a 2. Okay, and all I need are just really, I could have almost not even had those points, right? Because I just need even just 1 is enough, because I know what the shape is going to be. And we haven't worked with this graph very much, but the shape of a square root graph is start steep and levels off. So even if I just had that 1 point, I would basically know that I'm doing something like, well, that's not very good. You get the idea, something like that, right? Okay, so here it is. Okay, see how it works? What if that had been negative? What would it have done?
Flip it over the.
Yeah, would have flipped it over. And how could we have known that? Well, we could just pick one convenient point. The convenient point would still be this one, wouldn't it? It's going to be the one. It's going to be the one with coordinates 9, 3, and not because that's a 3, but because we started at 0 and it's a 3. Because we went over 9 and we went up by 3. So if I, once again, if I multiply 3 by negative 2/3 this time, we're going to make that a negative in a second. What's it going to do? Well, that's going to give me a negative 2, right? That's telling me something important. That actually includes the reflection in there, doesn't it? So it tells us both important things. It tells us what the stretch or the compression factor is, but because our result is negative, it tells us for the transform function, when I go over 9, instead of going up 3, I go down 2. So there's my point. And that's really all it takes to make my sketch, because I know what the basic shape of the curve is. And so if I change this to a negative, there it is, right? Okay, so now here's the next step. Here's the next step. So that's the stuff we talked about already. And I think people are getting the hang of that. Okay, so we said a couple things here. We said many things yesterday. But one thing we said was when we add a number to the output of the function, that's a vertical shift, right?
Yeah.
When we add or subtract a number from the input, that was a horizontal shift. Okay, let's make another connection with that. By analogy, if I multiply a function by a number, that's a vertical dilation, right? What if I multiply the input by a number? Horizontal dilation. Right, so let's try something then. So now instead of multiplying the function outside by a number, let's try multiplying the input by a number. Okay, let's multiply the input by 2. Okay, and let's see what that looks like. What did it do?
It doubled the next value.
Okay, it did something weird. Vertically, it looked like it stretched the function, didn't it? Right? Okay, let's go back to our other example for a second. We'll come back to this in just a moment, but let's go back to an absolute value graph for just a second here. Where is that one? Oh, what did I do with it? Oh, it's right here. This guy. Okay, let's get rid of that. And I'm going to change this one. I'm going to multiply. I'm not going to put the plus 1 on there yet. I'm just going to leave it an x. But we're going to multiply that by 2. Okay, let's look at what's going on here now. If I take this function, f of x equals the absolute value of 2x. I'm going to show you just a little something we haven't talked about yet. But if I take the absolute value of a product of two numbers, doesn't the absolute value mean that I'm going to find that product and make it positive?
Yes.
Okay, so what if A was -5 and B was 7? I'd have the absolute value of -35, which is 35, right? Couldn't I also, if I wanted to, just take the absolute value of each number separately? Would you agree? That's going to give me 5 times 7 is still 35. Okay, that always works, right? So we can always say if I've got the absolute value of a product, I can write that as the absolute value of the factors separately, right? So the absolute value of 2 times the absolute value of x. Well, what's the absolute value of 2? 2. Okay, so I could write this. This is exactly the same thing as saying that. Okay. It is for an absolute value function. It won't be for all functions. But I bring this up for a really important reason. everybody recognizes what is that? If I multiply the whole thing by 2, what did I do?
Double.
I doubled what? What did I do? I stretched it horizontally or vertically? Vertically, right? If I multiply the function by 2, I'm dilating it vertically by a factor of 2, stretching everything by 2. And we can see that. If I go over 1, instead of going up 1, I'm going up 2, right? Okay. But what about this? This you told me, and you were correct. If I multiply the input by something, that is a horizontal dilation, okay? Well, dilating it horizontally by multiplying by 2, and we'll talk about the details later, was equivalent to a vertical stretch. What is a vertical stretch equal to? Now think about, like, if I had a big piece of, let's see, this is make math more interesting. I've got a big screen up here made of taffy. And if I graphed an absolute value function on my taffy screen, and I pulled the screen upward to stretch it out, what's going to happen to the function? It would stretch vertically, right?
Yeah.
What's it doing horizontally? It's compressing, right? Everybody see that? Isn't that what happened here? I could either think about this as stretching it up vertically, or I could just as easily think about compressing it horizontally, right? Okay, but would you agree that a vertical stretch is the same thing as a horizontal compression? And a vertical compression must be a horizontal stretch? So they act oppositely, right? So then, what does this mean? If I put a 2 inside the function, a 2 outside the function means, that means vertical stretch, and 2 is the important number, right? If the 2 is inside, that means horizontal compression, right? 2 is also the important number though, right? If I'm stretching something by a factor of 2, that means I must be multiplying by 2. If I'm compressing something by a factor of 2, I'm dividing it by 2, which is the same thing as multiplying by 1/2, isn't it? So because they're opposite behaviors, whatever that number is inside, we have to do its reciprocal when we want to think about it, when we're going to find out what we're multiplying by, right? So in this case, this means when the 2 is inside like this means we're going to multiply by 1/2. And that works. Look at these points over here. If I were to write some convenient red points on this, look at how far they've moved horizontally normally and how far they've moved after the horizontal compression. I used to go over 1 and up 1. Now I only go over 1/2 to go up 1, right? I used to go over 2 to go up 2. Now I only go over 1 to go up 2. You see that? The vertical, all these points still line up vertically, but they've been squeezed horizontally, right? Instead of before where we'd say when you go right by 1, we're going to multiply the amount we go up, this time we're doing something different. This time we're saying when we go right by a certain amount and up by a certain amount, we're going to multiply a number by the amount that we move to the right, not up, right? So the point that used to have an x-coordinate of 2 is now going to have an x-coordinate of 2 times 1/2, right? The number that used to have an x-coordinate of 3 is now going to have an x-coordinate of what? The y-coordinate stays the same because we're compressing it horizontally. What's the x-coordinate going to be? If that used to be 3, 1/2 or 3/2, right? And it is. I go over 1/2 to get to that point right there, don't I? Right? You get the idea? Okay. So then, if I were to make this number inside, how about a 1/2, what's that going to do? That's going to be a horizontal stretch, right? Because the number I multiply is going to be the reciprocal of what's in front of x. So if b, we're going to call that b, by the way, right? A is the number we multiply by the function, b is the number we multiply by the input, okay? if b is equal to 1/2, we're actually going to multiply by 2. So now instead of going up 1 and over 1, we're going to go up 1 and over 2. Instead of going up 1 and over 2, we're going to go up 1 and over 4. Right? You get the idea? Okay, so now let's apply this to something like this. So what did we do there then? We took our parent graph, which is a square root, and if we multiply by 2 inside, what are we doing? So I'm multiplying inside by 2, right? That's the value of b, okay? So that means I am compressing or stretching?
Stretching horizontally.
No. Remember, it's the opposite. I multiply by a number bigger than 2 outside to stretch, right? But an outside stretch, a vertical stretch, is a horizontal compression, right? So it's the opposite. So because this number is bigger than 1, we're doing the opposite of the vertical stuff. Vertically, that would be a stretch, right? Horizontally, it's a compression. By how much? By 2, right? So tell me then, if I were to go out to 16, I normally would go up by 4 by going out by 16, right? That's a normal point on my parent graph, right? I've got the normal point over 16 up 4. If I do this to it, where's the point going to be? What's the number I'm going to multiply by in this case? What's going to be the dilation factor? If b is 2 and it's horizontal, what do I have to do to that number? I gotta flip it, right? Because it's going to be the opposite behavior. So this means I'm going to multiply by 1/2, right? Okay, so where is the corresponding point going to be on the green graph? 5.5 for this one? If I'm normally going horizontally 16 and vertically 4, right? This is a horizontal compression where we multiply the changes, the horizontal changes, right? So that's this change. We went over 16 and we went up 4. This is a horizontal issue, right? It's a horizontal stretch or compression. So we're going to multiply that number by the reciprocal of what's inside. Multiply by 1/2. So what's 16 times 1/2?
8.
Okay, good. So then instead of going over 16 and up 4, I'm going to go over 8 and up 4. Right? Does that work? Well, if I go over 8 and I go up 4, what do you know? There's a point on the graph. Right? Okay, normally I would go, in order to go up by 2 on a regular square root graph, I would have to go over to the right. How far? My input would be what for an output of 2? To get to that point, right? The square root of 4 is 2, right? So I would input a 4 to get out a 2. Coordinates of that point are 4, 2. Where's that point going to be if I dilate it like this? Instead of going over 4, how far am I going to go over?
2.
2, right? Because I'm going to multiply by 1/2, right? Instead of going over plus 4 and up 2, we're going to go over 4 times 1/2. We're going to go over, my color's wrong. I'm going to go over 2 and up 2. You see that? Okay? All right. So see if you can, I'm going to give you one to do. Try this. If you can do this, you got this whole chapter just completely under control.
Getting close to forward. Being a good student.
Okay.
Alex, there was a 94 four-door Honda Accord sedan, just twin turbo. That was hilarious to watch. It was front-wheel drive twin turbo.
Okay. Okay, try this. Everybody try that. Get out of your notebook. I got graph paper. If you need graph paper up here, I want you to try to see if you can do this one.
Dude, that's fancy. Yeah, boy, that was pretty hard.
It looks hard, but it's not so bad.
Yes. Okay, real quick, what's going to be? Okay, what's going to be the parent function here? What kind of a function is this? It's a square root. Okay, so our parent graph is square root of x, right? So what's f of x going to be, right? If we're going to tweak this thing, we're going to do a square root of b times x minus h plus k. Now notice the b, we haven't done a translation yet, but I've got to multiply whatever this horizontal dilation factor is, I've got to multiply it by the whole input, which is x shifted, right? By the whole x minus h. So what do these things do? H and k is still the same as before. H and k are going to be the coordinates of what point for our square root graph?
-5, -4.
Say it again.
Is that the vertex?
It's going to be that initial point, the one that starts off at the origin. So that's going to be our initial point, right? Which is like a vertex, special point, right? So we already know where that's going to be, right? It's going to be at where? What are the values of h and k? -5, -4. Okay, so we know that the initial point is at -5, -4. But what about this? That's the value of b, right? Okay, so if b is 4, what are we going to multiply by horizontally? We're going to multiply by what? 1/4, right? We're going to multiply the horizontal changes by 1/4. Okay, so if we go to, this probably isn't the right answer, but we'll just use this graph at least. So if we go to -5, -4, right? Let's pick one let's pick that one. Okay, so our vertex is at -5, -4, so there it is. Right, our vertex is going to be -5, -4 right there, okay? Normally, we would go over one.
Did you rest me for advisory tomorrow?
Yes. Yeah. Normally, we would go over one and up one. We'd go over, what's another point on a square root graph? On a square root graph, right? If it's square root, normally we would go over one, up one, over 4, up 2, right? We go over 4, up 2.
Oh, then over 9 and 3, right?
Over 4, yeah, good. Up 2, we go over 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and up 3, right?
Yeah.
And that's going to give us our normal parent graph. But now, what if I'm multiplying those horizontal changes by 1/4? Where's a convenient one? What's a horizontal change that's going to play nicely with 1/4? Not 1. 1 times 1/4 is 1/4. Not 9. 9 times 1/4 is 9/4. 4 looks pretty good though, right? If I multiply 4 times 1/4, then that means that this point right here is going to get scooted clear back to there, isn't it? Right? Because instead of going over 4, we're going to go 4 times 1/4, which is 1. We're only going to scoot that way by 1, right? So my graph is just going to look like that, right? That's all we need, is one point that we know it goes through and the vertex, and we got the function. So we want the one with a vertex there that's going to go over 1 and up 2, right? So which one is that?
Not that one.
Well, I believe so.
Not that one. Not that one. That one right there, isn't it? Oh, not quite. No, not quite. No. There it is. Right? -5, -4, over 1 up 2. That's it. Right? Everybody see it? Okay. That's a lot of stuff for, I mean, I'm going to give you an assignment to practice on this tomorrow. But give me a 1 to 5 on this. Vertically, before we got to the B stuff, just vertical compression stretches. Don't worry about the B's, but just everything up through this, up through what we did today. I want to get a 1 to 5.
Oh, up to today, that's a 5. Just today.
Give me a 3.
Okay. Now horizontal stuff.
Oh, that's a
That's
definite
like
2.
a 3.
Okay, that's all right. It's first day. That's good. Okay. All right. All right. I'll take